I will provide a very short key or suggestions for each problem of the chapter 5 homework problems. Here's a problem to figure out the molar mass of hemoglobin, and we are using the ideal gas law to do so. By definition, the molar mass of hemoglobin is equal to the mass of hemoglobin divided by the moles of hemoglobin. Now, if I look at the problem, I can see, the mass of hemoglobin is directly given. But what is not given is the moles of hemoglobin, so we need to figure out the moles of hemoglobin. How do I do this? Well, I know there's a mole-mole ratio between hemoglobin and O2 that is 1 to 4. And I also know that for O2, this part here, I'm given ideal gas law information. So I know PV is equal to NRT. I solve this for N, which is PV over RT. And now it's just simply a plug and chuck thing where you just change the pressure to ATM using 760. And you change the milliliters to liters and the Celsius to Kelvin. And if you do, you should get 784.8 divided by 760 times 1.48 divided by 1000 divided by 0.0821, which is my R value, times 37.8 plus 273. And if I plug this in, I'll get the moles of O2. Now, how do I go from moles of O2 to moles hemoglobin? That's a factor 4 to 1 that I have to include. So I need to divide my moles by 4, gives me the moles of hemoglobin. And then you just calculate your molar mass. And in this case, you will simply have 1.045 grams divided by 1/4, because it's a 4 to 1 ratio. And the mole, if I do all this in my calculator, you should get something like 5.99 times 10 to the minus 5. So this is about 5.99 times 10 to the minus 5 moles. It's very small. And that's approximately, if I calculate this, that's approximately 70,000 grams per mole. So you guys have, of course, different numbers, but this is the way to solve this problem. In this problem, we can see there's a sample of sodium azide, and that sample decomposes and produces nitrogen gas. And this nitrogen gas basically fills the airbag, which then prevents any damage to the passenger. So let's take a look how to solve this problem. First of all, we need, for every chemistry problem that involves some sort of stoichiometry, which means calculating from the mass of my reactant, the gas or moles of my product, I need a balanced chemical equation. So let's start with a balanced chemical equation. Sodium azide decomposes into its elements. And obviously, this is not balanced. So we need to introduce the coefficients here to make this equation balanced. Now I have 53.878 grams of sodium azide, and I want to know what is the volume of N2. And I want them kind of below the chemicals in the balanced chemical equation. So my thought process is convert this into mole of sodium azide, then use the coefficients to get the moles of N2, and then we're going to use ideal gas law. Now let's do the first step. 53.878 grams divided by the molar mass, which is about 65 grams per mole. That gives me the moles of sodium azide times Well, divide by where you are, 2 moles of NaN3 and multiply by 3. That gives me the moles of N2. In this case, the number should be about 1.24 moles of N2. And then we know ideal gas law, right? PV is equal to nRT. Volume is nRT over P. And if you look in the problem, this is the pressure, this is the temperature, these are the moles, and the R constant is a given constant, so you should be able to calculate the volume. The volume in this problem here. In this problem here, we're mixing two gases and they react, forming a product gas. And from the initial and final pressure, we have to figure out how much SO3 is formed. So let's take a look how to solve this problem. Let's first start with a balanced chemical equation. Well, you place, so you have an SO2 gas that reacts with O2 and forms SO3 gas. And when you balance this, you can see you need some coefficients here. And now that it's balanced, we're going to write down our initial conditions. So initially, we have the pressure of SO2 initially. I don't know what that is. We have the pressure of O2 initially, partial pressure, don't know what that is. And the pressure of SO3. And I know that the sum of all those three pressures is equal to 2.30 atm. That's the sum of the pressures initially. Then you have a change. I'm going to put a delta here for change, and then I have a final pressure. And the final pressure depends on the change. Now, here's the tricky part. For every 2 moles of SO2 that are used up, I need to use up 1 mole of O2. How do I write this mathematically? For example, minus 2x. So for every 2x of SO2 that's used up, 1 mole of O2 or 1x of O2 is used up, forming 2x of SO3. So basically just the coefficients times x, because I don't know exactly how much is used up. Then my final is obtained by summing these things up, right? So that's the pressure of SO2 initially minus 2x, the pressure of O2 initially minus x, and this is just simply 2x. But I know that the sum of this the sum of this is equal to 1.26. Now, that is really useful because now I can use this final equation here and rearrange. So the pressure of SO2 initially minus 2x plus the pressure of O2 initially minus x plus 2x is equal to 1.26. Can we write this? And if you look, this here is the same as the sum of the initial pressures. So this is 2.3. Then these guys here summed up is just simply minus x, and this is 1.26. Now what you can do is calculate x, which is the pressure, the partial pressure of SO3 formed. And then we know we can convert this partial pressure into moles. And in order to do so, of course, we need the volume, the temperature, and the pressure. So this is pressure, volume, and temperature are all given, and then you can just simply calculate the moles using ideal gas law as a constant. This problem here is an interesting problem, and when I imported it into the software, the images kind of overrode the text a little bit, but you have it on canvas, so you should know how to solve this problem. I just, maybe for clarity, say this should be 15 milliliters, this should be 0.012 molar, and this is asking for the volume percent of SO2 in the sample. So keeping that in mind, let's see how we can solve this problem where we take a contaminated air sample. This is contaminated air sample, so that means we're going to have some air with some other stuff in there, in this case sulfur dioxide, and we want to know how much sulfur dioxide is in there, and is it toxic level basically, right? In order to do so, we're going to calculate the volume percent. Now let's take a look at this problem. By definition, the volume percent of SO2 is equal to the volume of SO2 divided by the volume of the sample times 100. Now, let's take a look. The volume of the sample is already given. It's right here, 520 milliliters of sample. So that is given in milliliters. And the only thing left to calculate is the volume of SO2. Now, here comes in our knowledge from the first part of the class, because we have two reactions here. So we have SO2 plus I2 plus H2O reacting. That's reaction 1. And then reaction 2 is the iodine reacting with a thiosulfate. That's the second reaction. And both of them are unbalanced. So of course, the first thing we should do is balance those equations. So in order to balance it, it's very clear that the bottom one here need 2 2's to balance it. So now this bottom one is balanced. And the first balance the first reaction, you might want to use half reaction method, but it's not really necessary, because if you see there's I2 on the left side, so on the right side you need 2 of them. There's one sulfur. So, but on the left side there's 2 oxygens, so on the right side there's 4 oxygens, so I need 2 water to get 4 oxygens, which leaves me with 3 H pluses. So now both of them are balanced. Now we need to think about the science part. How do I get the volume of SO2? Well, in this case, that is very simple, because basically what we do is we have an indirect titration, okay? So we're having a sample, and to this sample we're adding iodine, okay? Now, iodine is I2, and when we add this to the sample, the iodine reacts with the SO2 in air. How much? All of it, because this should be the limiting reactant, the SO2. But there's leftover iodine. Now the leftover iodine is titrated with sodium thiosulfate, and that is kind of hidden here under the balanced chemical equation. So this will give me the moles of S2O3 2 minus, and from the moles of S2O3 minus I get the moles of leftover I2. So this will give me the moles of leftover I2, and from the total and the leftover I can get the moles of SO2 that was originally in the air sample. So let's take a look how this works mathematically. So the total mole of I2 is pretty much molarity times volume, which is 23.29 divided by 1000 times 0.013 in this problem. And that is approximately 3.03 times 10 to the minus 4 mole of I2. Okay, perfect. Now, we know that the moles of I2, some of it reacted with thiosulfate, and some of it reacted with the SO2. The ones that reacted with the SO2, that's the mole we're interested in, but now we need to first calculate the moles of I2 that were left over, and that we get from reaction 2. And it's simply 1/2 because there's a 2-to-1 ratio here. 1/2 times the molarity of thiosulfate times the volume of thiosulfate, which is 15 divided by 1000 liters times 0.012 molar. And it's simply about 1.8 times 10 to the minus 4 mole of I2 that was left over. Now, in order to get some information here, we look at those two numbers and we know we need to subtract them. So we can calculate the moles of I2 that reacted with SO2. And that is just the difference between them and if you calculate the difference of moles of I2, then you can see that gives you the moles of I2 that reacted with SO2, and that is the same as the moles of SO2. So that is great because that's the same as the moles of SO2 in my air sample. And then how do I convert moles into volume? Ideal gas law. And you have all the information. You have the moles right here. So this here is the moles. And the temperature is right here. That's my temperature. And then of course this here is my pressure, which is right there. And you should be able to calculate the volume of SO2, and then you should get the volume percent. This problem here is a pretty difficult problem for students to comprehend and might be too long for an exam, but it should still be something that you can be able to figure out. And the power is here that we can relate the depth of how deep a diver goes. So there's this depth. We can relate this depth, so this increase in depth, we can relate this to pressure. But somehow we only know how to measure pressure in units of Hg, millimeters of Hg, but we're given information of seawater and seawater depth. So somehow we can relate the depth in seawater to a pressure using this information about the 760 millimeters of Hg is equal to 1 atm. So let's take a look how we do this, and this is quite complex, so stick with me, okay? So basically I have the surface, and at the surface we have 1 atm. So I have my diver here at the surface, and at the surface the pressure will be 1 atm. And then the diver dives down a specific depth. And of course, there's another pressure down here at a depth of 148.8 feet. There's another pressure, and I don't know what the pressure. Now in part 1, I'm going to show you how to calculate this pressure. So now we assume the scuba diver is all the way here at the bottom. He got there safely, and it took a long time. So he's safe, but his lungs have changed in volume because the pressure has changed. Now the scuba diver wants to go back up, and he wants to do this very fast. So if you do it slow, that's no problem. You give yourself time, you can get all the way back up to the surface. But if you do it really, really, really fast, then because of the pressure changes, your lungs can rupture. Now, what tells me how far I can go? Well, this factor of 1.7. This is the ratio between pressures. So that's the ratio between, let's say, diving to here. So that's the pressure where you rupture, compared to the pressure at the depth that I calculated. So these two pressures, if that ratio is 1.7, then your lungs rupture. So depending on this ratio here, that tells you how high you can go. Can you only go till here, or till here, or till here? That depends really on your lungs. And this limiting factor of your lungs and how high you can go, or how close to the surface you can go really fast, that we will do in part 2. So in part 1, we'll go down 148 feet down. So we go down 148 feet. And then in part 2, we want to go up really, really quickly, but only so our lungs don't rupture. So how high can we go? Can we go 50 feet? Can we go 100 feet? Or can we go all the way back to the surface, which is about 150 feet? Now, that is determined by this ratio, and so let's do a calculation for part 1 first, and then we'll take a look at part 2, what happens. Okay, here's part 1. So the first thing we're going to do is we're going to look at the depth. And that was 148.8 feet. And we're going to multiply this by 12 inches per feet times 2.54 centimeters per inch times a factor of 10 millimeters per centimeter, which would basically give me a height in seawater of about 45,354 millimeters in seawater. Now, if you think of a mercury barometer, so it's a mercury barometer, then the height of this column, 760 millimeters of Hg, corresponds to 1 atm. Now, if you think about this fact, and the fact that, well, in this case, we are diving down in seawater, you can ask yourself, what would be the height if instead of mercury I would use seawater? And obviously that height would be much smaller. Why? Because density of mercury is much different than density of water. So when it experiences the same pressure and fights against gravity to get to this equilibrium of 1 atm, you don't have to go 760 millimeters of seawater, you have to go a different distance. So basically what I'm trying to do is convert this into millimeters Hg. And how do I convert this? Well, I know that the depth of seawater is related to the depth of Hg, and the things that help me relate this are the density. So density of H2O and density of Hg. So then basically the depth or the difference in pressure here of Hg is simply my depth of water times the density of water divided over the density of mercury, which in this case is 45,354 millimeters times the ratio of densities, which is 1.025 divided by 13.91, which in this case is 3,342 millimeters of Hg. Now, this little trick helped me to convert this depth into something that helps me relate to ATM, because we know there's a factor 760. So if I take this number and divide by 760, so the pressure of Hg is basically 3342 divided by 760 in ATM, which gives me about a pressure of 4.4 ATM. Now let's relate this to the diver. When the diver's at the surface, he has 1 ATM. When he's at the bottom, or when he's down 150 feet about, then the pressure increase is 4.4 ATM. So at the bottom, he should have 5.4 ATM. Now the scuba diver will make an assumption here, and will make the assumption that the lungs stay the same temperature. You know, you have a wetsuit that protects you from the cold water. So basically, when you're at the bottom here or at the top, the temperature of the lung is constant. So say temperature of lung is constant. Well, also the moles are constant. And if the moles and T are constant, then we know P1V1 equals P2V2. And if you rearrange this, then you can write that V2 over V1 is equal to P1 over P2. And 1 and 2 are just arbitrary. That could be initial, final. You can use this as whatever you want, but this is basically 5.4 divided by 1, which is 5.4. So now let's take a look at part 2. And in this case, we're down at the bottom and we want to ascend, meaning dive up to the surface. And the question is, hey, how high can I dive up to the surface? Basically, my ratio 1.7 is equal to the ratio of two pressures. And what are the two pressures? The two pressures are the pressure at a depth of 148 feet that we calculated, divided by the pressure, which we don't know, at which your lungs will rupture. The pressure at 148 ATM we already calculated, which was 5.4 ATM. So now we can calculate the pressure at which it ruptures. This is my x. Well, in this case, that's pretty straightforward. And the pressure of rupture is equal to 5.4 ATM divided by 1.7 ATM, which is equal to, in this case, 3.175 approximately. Okay? Now, that is the pressure to which we can ascend. So if here's the pressure 5.4 ATM, then we can ascend to a pressure that is 3.175 ATM. Now think for a second. How can I relate this difference in pressure? How can I relate this to depth? And again, we know we can relate depth to difference in pressure using the 760 mmHg and the ratio and density. So let's calculate the difference in pressure first. Now the difference in pressure is 5.4 ATM minus 3.175 ATM, which is about 2.23 ATM difference. Now convert this into depth if we use this factor of 760 mmHg. Well, if you use this factor of 760 millimeters Hg, then 2.23 times 760 is equal to 1691 millimeters in Hg. That's not so useful because we are not diving in millimeters of Hg, but we can relate to millimeters of seawater using the ratio of densities. So that is pretty straightforward, because now what we can do is we can take these millimeters and convert it to millimeters of Hg. So 1691 times the ratio of density, which was 13.91 divided by 1.025, gives me the millimeters in, and in this case that's about 22,948 millimeters in seawater. And of course you can convert this by from millimeters into feet. So let's do this quick conversion. And we can use a conversion factor that 1 foot is equal to about 304.8 millimeters. So 22,948 divided by 304.8 gives me the length in feet, and that is about 75.3 feet. So basically, once you're down 148 feet, you can dive up 75.3 feet, but not to the surface. Because if you ascend any higher than 75.3 feet quickly, then your lungs are in trouble. So this is how you solve this problem. We use the same trick of relating the densities to depth and relating the densities of seawater and mmHg to convert a depth in seawater to a change in pressure. And we make the assumption that the moles in your lungs and the temperature stays about the same.